Hello, and welcome to another lecture for ME 372 Machine Design. In this lecture, we're going to continue talking about systems subjected to combined loads. So we've looked at this example several times now, where we have a cantilever beam with an axial load, a transverse load, and a torque. And then we are asked to compute the stresses that act back at the wall on the top of the cantilever beam at an element A and at the side element B. So we know the steps to this are to draw a free body diagram of the structure, label a coordinate system, and draw on the reaction forces and moments. So in some situations, we will need to use shear moment diagrams to determine the critical location. But in this cantilever beam example, we know the critical location is at the wall. So I sum forces in X and realize that I have an 8,000 pound or 8,000 Newton load pulling in the negative X direction. In Y, I have 550 pushing up. And in Z, I have no loads, no forces. Then I sum moments, and I have a moment at the wall, so I call that the moment at the cut. I have an applied torque, which is the 30, and it's in the positive I direction, plus R cross F, where R cross F represents all the forces that occur out here at this point. So my R cross F is IJK. Then I go 100 millimeters in the X, 0 in the Y, and 0 in the Z. And I have 8,000 newtons applied in the X, minus 550 in the J, and 0 in the K. And I solve this cross product and get minus 55K. And then I come and draw these forces and moments at the cut on my beam. And now if I look at these as review, I can see that this 550 is coming up along the side of element B. So this 550 newtons is going to cause a VQ over IT shear stress, a transverse shear on element B, but it's not parallel to any of the cut edges on element A, so it won't do anything to element A. Here, this 8,000 is pulling on element B. It's normal to the cut edge here at B, and it's normal to the cut edge at A. So this will be as sigma equals P over A stress for both element B and element A. This 30 Newton meter torque is trying to twist the beam, and so putting my thumb in the direction of the arrows, I can see that the arrows would be going up along this side of B and also up along that side of A. And so that distinguishes the direction for the torque. Then here, this bending moment, I can see that B is at the neutral axis for the 55 Newton meters, and so it will not cause any stress on element B, but it would put element A in tension. So hopefully you can look at these loads now and come up with these stress elements and identify the directions and the magnitudes of the stresses. We then looked at this example. Well, before we went to the next example, here's a summary of how to treat the forces. So these are reaction forces. So assuming that this body was loaded somewhere such that we computed these reaction forces, this is how these reaction forces would cause stress on element A, where element A is on the front of this cylinder. Element A is positioned on the front of the cylinder. And so in the X direction, I have a negative F1. In the Y direction, I have F3 pushing up. And in the negative Z direction, I have F2. So if I come now and look at element A, I can see that this F1 is parallel to the cut edge. It's parallel to that cut edge of element A, so this is going to cause VQ over IT, where V would be F1. F2 is piercing through element A, so Q would be 0, and so F2 does nothing to element A. And then F3 is pushing up on the cut face. So it'll be a P over A. It's normal to the cut face. It's normal to that cut edge. And it's pushing on it in compression. So it'll be a compressive P over A. When we look at the moment, here we have an M1 about the positive X. Here we have an M3 about the positive Y. And here we have an M2 about the positive Z. If I look at what M1 does, M1 is going to cause a bending stress on element A. And this bending stress will put element A in tension, because if I put my thumb in the direction of the X, my fingers would be coming out of the bottom of this cut edge and up into the back of the cylinder. So my fingers coming out of here would represent that this is in tension. This M3 is going to cause a torque, and I slide this direction down to the cut edge, so it's going around this way on the cut edge. So my torque TC over J is going to be coming around this way, as given by this arrow here. This M2 is bending the shaft, but element A is at the neutral axis for M2, so M2 will not cause any stress on element A. We then looked at this example here, and we had this signpost in a windstorm. We determined our reaction, or our applied loads, were the weight of the sign pulling down at 500 and 576 pushing in to the paper, 432 for the wind on the post, and then a weight of 392 down here. So I sum forces and moments, and I get these reaction forces and moments acting on element A, and I come through and ask which each one of these will do. Here I can see that the 892 force is pushing up on the cut edge at a 90-degree angle. So this 892 here will be putting the element in compression. So that sigma equals P over A at 892, and it's this number 2 force arrow representing the stress shown here. Then I can look at this bending moment, and this 78,624 is going to be putting element A in tension. That's this number 1 shown here, and it's MC over I. The 8064 is, if I put my thumb in the downward direction as shown here, my fingers would wrap across the cut edge of element A in this direction as shown by this arrow here, and I'd have a TC over J of 8064. The 7000 is at the neutral axis for element A, and the 1008 pierces. We now want to look at another example of a combined loading problem. In this example, we're going to look at a bracing bit as shown here. A bracing bit is a device that is used to drill holes in materials that are usually soft. It's a hand-operated device, and it's operated by pushing here on the handle to apply a thrust while turning this part of the handle to generate a torque that will twist the drill bit and drill a hole. In this example, a company has designed and manufactured a bracing bit, but it has had problems with them failing. The instruction manual tells the users to not apply more than 150 inch-pounds of torque and 50 pounds of push load. In a typical scenario, the bit has a shank diameter of a 1/2 inch and it extends about 3 inches from the wood to the chuck at the start of the drilling process. So here is my plate where I'm drilling the hole. Here is the chuck where my drill bit is mounted, and here is my drill bit, and it is shown to be 3 inches long. It says the device has been braking at section AA, and we are to determine if the diameter at this location is sufficient to carry the loads. So we need to come in and analyze the stresses at this point here and determine if the shaft at that location is large enough to carry the applied loads that are generated when drilling a hole. So to solve this problem, we're going to do like we should do in all the other problems, and that is begin by drawing a free body diagram of the system, labeling a positive coordinate system, and then summing forces and moments. So coming to the next slide, we can see that I have drawn a free body diagram of the system. Here at point A is where the thrust load will be applied. Point B is where the bracing bit makes a bend, and C it makes another bend. Point D here is where the force is applied to generate the torque. Then we come over to point E. Section AA is defined by point F. Point H here is the chuck, and then point O is where the drill bit goes into the wall. We can see the dimensions are given here, and we can see that a coordinate system started at the wall has been developed. So this is my X direction, this is my Y direction going vertical, and then my Z direction coming out of the plane. So now we can begin to look at putting this system in equilibrium. And we do that by summing forces and moments. And this is where the real engineering challenge is generated, and where we really need to think about the system that we have. So it says that we had a torque of 150 inch-pounds. So back here at the wall, we're going to have a torque of 150 inch-pounds. And I've noted that as TO, the torque at point O, in the X direction. And it is positive with our thumb going in the positive X direction, and its magnitude is 150 inch-pounds. This torque is generated by a hand pushing on point D. So up here at point D, we need a force, FD, in the Z direction that will generate this torque. So this FDZ will be going in the negative Z direction, and it will generate this reaction torque, TOX, here. The 50-pound thrust load is applied by the hand at point A. So here at point A, we have an FA in the X direction, and we put it in the negative X direction because we want to push the bit into the wall. So writing summation of forces, we know that we will have to have a reaction here at point O to resist FAX, and it will be going in the positive X direction. So we have ROX in the I direction plus ROZ in the K direction, and we put that in this direction because we know it will counteract what's going on here with FDZ. Then we have minus FDZ in the K direction plus FAZ, and this one is a little bit hard to recognize if you're not careful. We know that for a drill bit, we want to have the summation of moments equal to 0 back here at point O. You've probably all broken a drill bit before, and that's because you've applied a moment, a bending moment, to the drill bit. And so if we have a bending moment applied here at this point O, we will break our drill bit. So we need our summation of moments at this point here to equal 0. And in order for that to happen, we can see that this FDZ is trying to twist the bracing bit around the y-axis. So we have to have an FAZ out here at point A to counteract the FDZ when it tries to create a moment. So the user will actually apply the FAX here as well as an FAZ. There isn't any other location on the bracing bit where a force in the Z direction that would counteract FDZ could be applied. And this is where the understanding of the problem and the real engineering comes into play. You need to recognize as an engineer that this FAZ is actually an applied load by the user, but it certainly wasn't given in the problem statement. We determined that FAZ needed to be there by understanding the problem and understanding that summation of moments here had to be equal to 0. And with this FDZ trying to twist me about the y-axis, I had to have some other force keeping me from bending about that axis. So now I can group terms, and this is pretty easy to determine these reaction loads. We know that ROX will be the 50 pounds. Grouping terms in the K direction, we get this expression here, where ROZ minus FDZ, this is going in the negative X direction, plus FAZ equals 0. So that's all I can do with summation of forces right now. Now I need to turn and look at summation of moments. And so I have the moment at point O, and this moment right here will actually be 0. So I put it down there to note that I have thought about it, and then I typically cross it off if it's 0 and show that it goes to 0. Then I have the torque, TOX, which is this reaction torque, plus, now I go to the points where forces are applied and put an R cross F. So I'll have an R cross F to point D plus an R cross F to point A. There aren't any other locations where forces are applied, so this is my total moment expression right here. I know that TOX is 150 inch-pounds because that's what was given. Now I look at the details of R cross F to point D, and I write down IJK for the unit vector directions, and then to get to point D from point O, I go 9.75 inches in the I direction, and that's a plus. Then I go plus 5 inches in the Y direction, and I go 0 inches in K. The only force I have acting at point D is FDZ, and it's actually acting in a negative direction. So I have 0 in X, 0 in Y, and minus FDZ in the K. Solving this cross product, I get this expression here. I then turn to the R cross F to point A, and I go 15.75 in the I direction, and then I have 2 point loads out there at A. I have an RAX with a minus sign because it's in the negative X direction, and I have an RAZ, and then I can solve this cross product. Now coming down and solving for my moments and my applied loads, I can get this summary. The reaction force in the X direction at the wall is 50 pounds. In the Z direction is 11.43. FD turned out to be 30 pounds. FAX is 50 pounds. And FAZ is 18.57. So now I can go back and look at my system, and I've determined magnitudes for all of these forces and moments, and my system is in equilibrium. Now I can take these applied loads and I can cut my system, and I can look at this half of the system, or I can look at this half of the system. And in this example, I actually show you how to do both, but we will first look at cutting the beam here at section AA and looking in this direction here. And so doing that, I'll redraw a free body diagram and label the forces. So here's my point F, here's my 30 FDZ, and here are the loads applied at point A at my handle. We determined they were 18.57 and 50 pounds. And the directions are also shown. So now what I do is I sum forces and moments at this point of interest. So summing forces, I have FFX, which is going to be positive, counteracting this negative 50 pounds. So I know that FFX is equal to 50. Then I can write in the Z direction, this 30 is pushing in the negative Z, this is pushing in the positive Z, and so for this to be equal to 0, or for that sum to be equal to 0, I know that FFZ needs to be in the positive direction as well. So summing forces there tells me that FFZ is equal to 11.43 pounds. So I now know my forces, my reaction forces here at point F. Now I'm ready to sum moments. Now the summation of moments has to be equal to 0, but the moment of F will certainly not be 0 in this case. This point here can handle bending and twisting and carry moments. So the summation, this moment F will not be equal to 0, like the MO was when we summed moments about the wall. So summing moments here, I only have, again, two places that external loads are applied, and I have no external torques. So I'll have an R cross F for point D here, and I'll have an R cross F for point A here. Now summing or getting the details of R cross F for point D, going from this point F, I have 3 in the I, 2.75 in the J, and 0. And the only force here I have again is the minus 30. Then I go to point A, and to go from point F out here to point A, I go 9 in I and minus 2.25 in J and 0 in K. And again I have two forces out here. I have a plus 18.57 and a negative 50. So solving for my moment at point F and these cross products and combining all those terms, I see that the moment at point F is a positive 124. Applying the forces and moments that we computed on the previous page to a free body diagram results in this figure shown here. We have our 50 in the X direction, 11.43 force in the Z direction, and then our moments and torques. Now to look at the stress elements, I'm going to look at stress element A on the top of the shaft, or here in the front of the shaft, and element B is going to be right behind element A on the back, or the bottom of the shaft. So coming here and looking at the 50, I can see that that 50 is crossing through element A parallel along to this cut edge in this direction. So that's going to be a VQ over IT shear stress. Since I have a circular shaft, it's 4/3 V over A. So here's my 4/3 V over A, and the V is 50. Then I look at the 11.43, and the 11.43 is going to be coming right out of A. It's going to be piercing through element A, so Q is 0, and the 11.43 doesn't do anything to the stresses at element A. Now I look at the 112.5, and element A is at the neutral axis for the 112.5. I then look at the 77.5, and this 77 is coming around in this direction here, so it would be coming across element A in this direction, going from the left to the right. So coming down here, I have a TC over J, which is given here, where the T is the 77.5. And in this case, the TC over J and the VQ over IT add together. I then look at the 124.4, which is bending the shaft, and it's going to be coming out of the bottom of element A and up into the back of the shaft. So it will be putting element A in tension with an MC over I, and the moment is the 124.4. Now if I look directly behind this shaft and looking straight into it, I would see B like this. This bending moment due to the 124.4 will actually be in compression. You can see that the VQ over IT shear stress now has changed sign, and this 11.4 or the 50 here will be going across element B in this direction here. And so that will be the VQ over IT stress. And my TC over J is going in the same direction as it did up here for my element A. So the bottom or the back side of the shaft for element B would have the stresses in this direction. If I now look at elements on the left side and the right side, I can compute and determine the stresses that act on those elements. For elements on the side, we'll look at the right side, and this 50 will pierce through the element. So this 50 won't do anything to the side elements. The 11.43 is parallel to the cut edge. So it will be coming parallel to the cut edge and cause a VQ over IT stress. In this case, for the 124.4, elements on the side are at the neutral axis, so this bending moment will not cause any stress. Whereas the 112.5 will cause tension over here on the left side as it comes out of the element, and then compression on the right side as it goes in to the right side element. And the 77.5 torque will come around and cause the shear stress as shown here. So hopefully this example clarifies a lot of how to put an entire system in equilibrium, then cut the system at the point of interest and determine the reaction forces and moments, and then once they're determined, draw those stresses that act on a stress element. One more part of this example problem is shown here, where I have taken and made a cut at point H, and we have these reactions at the wall. So here are my wall reactions. This is the end of the chuck, and these are the reaction torques and forces and moments that occur at the chuck. And I can determine values for those from these expressions here, and then I can come and apply these forces, moments, and torques to an element A, and these are the